So, welcome back everybody after the break for this second session. Now, in the first session, we have looked at the very basic things exponential smoothing, uh, forecasting, and we have got a fair idea about what trend is, how trend is incorporated, or what seasonality is, and how these trend and seasonality components are separated out from the original data. Now, here are some examples or the graphs that are seen on the screen. In these graphs, do you have any specific observations which would talk about some similarity or dissimilarity or differences between these underlying data sets? Say somebody can tell that. Okay. So this is the data that we have already seen, which is the CO2 concentration data. And as we have observed, there is a trend present in this data as well as seasonality is present in the data. And if we see the changes which are observed in the time series data, or maybe we can say the fluctuations or the variations which are happening in the data set, they are lying within certain range. Okay. And if you try to draw a line from these data points, from the midpoints of these data points, which is called as which is the series level value, passing through the midpoints of these uh, actual data points, then it's a slanting line. It's not a straight line which is parallel to the x-axis. Now, same way, if this second graph, if you observe in this data set, here, if you see, if you try to draw a line through the midpoints of the data values, it is approximately parallel to the x-axis, and the fluctuations that are happening, they are around 0. Sometimes the fluctuations are between -10 to +10. Sometimes the fluctuations are very high. It's -20 to 20 or -30 to 30. But the values are around 0 itself. Same thing can be observed in this data set, second data set on the um, second line. The fluctuations are around 0, and the fluctuations which are happening are almost within the same range all throughout except at 1 or 2 points. So here what we are observing here in this first data set, which is the graph of CO2 concentration itself, but the fluctuations which are happening, they are not around any particular value, or neither we can draw a straight line to that or a curvilinear line, but there is no regular fluctuations or systematic fluctuations which are observed in this data point, in this graph. Again, here are some more examples. So in the first graph, you can see the values are increasing. So the trend is present, but as well as the fluctuations which are present in the data, they are increasing over time. The range of fluctuations is not same. As against that, here in this data set, the trend is present very clearly, but the fluctuations are same all through the time point. In the third data set, again, the fluctuations are around 0, but the magnitude of the fluctuations is different. The last graph, you can see the fluctuations are around zero, as well as the magnitude of fluctuations is same all through the time points. So we can see this difference between all these graphs that we have observed as per the fluctuations, the mean fluctuations, and the magnitude of the fluctuations. And this talks about mean stationarity and variance stationarity of the data. So mean stationarity is when you have the values of the time series over all time points fluctuating or moving around a same value, and variance stationarity is the magnitude of the fluctuations is same for all time points t. Now, why do we require this assumption of stationarity in time series analysis? Is for the inference purpose. As we all are aware, we need replications, and in time series analysis we have only one observation at a single time point. So for the inferential purpose, generally it is assumed that the values have same mean across all the time points. Okay, and this is achieved by the assumption of stationarity, which is mean stationarity and variance stationarity. So in this data set, as we have, this is one of the graphs that we have seen previously, the values are around same mean, which is zero, and the fluctuations or the magnitude of the fluctuations across all the time points is also same. So this data set can be considered or treated as mean stationary as well as variance stationary. Now, can anyone tell me about whether this second graph that we are seeing on the screen, whether it is mean stationary and or variance stationary? So as we see, these values are increasing over time. The fluctuations are not around zero or around constant value. Hence, this data set can be considered as not mean stationary, but this is variance stationary. The magnitude of variability or the changes at every time point is same all through the um, time parameter. And in this example, as we see, this data will be mean stationary but not variance stationary because the variability is increasing over time. Now, the methodology that we are looking at in this, we require the assumption of stationarity, which is called as this Box-Jenkins method of forecasting, and the weak stationarity talks about the mean at time point t is same for all t. Variance of the at time t, it is same again for all t, and the covariance between yt and ys, it is a function of the difference between the time parameters t and s, which is called as the lag. Okay, and the autocorrelation is defined as the correlation between the same variables which are apart k time points apart from each other. So this k time points apart is called as the lag k. So rho k is the correlation of yt and yt minus k. And if you plot the graph of rho k versus k, it is called as the autocorrelation function. Okay, and if we have a stationary series, so since the covariance is function of the lag alone, stationarity implies that autocorrelation is also a function of lag. And this is the basic requirement when we go ahead with the Box-Jenkins methodology. So for any given data set, we have already seen that seen different data sets previously, and all these data sets are not stationary always. So you need to make the data stationary. So for making the data making the data mean stationary, what you need is the differencing. Now, differencing, as the name suggests, it is the differencing of two values. So it is the current value minus the past value. And since it is the differencing between two consecutive values, it is called as the non-seasonal differencing. Uh, Same way, if the seasonality is present in the data, you need to make the data stationary in seasonal index as well. So the current time point minus the previous time uh, same season observation will give you the seasonal differencing. So these are the notations which are used, and this is first order differencing. Now when I am saying that this is first order differencing, you definitely have a second order differencing as well available. So it is the difference of the first order difference series. So if you are using first order non-seasonal difference series data and difference it once more, it will give you the second order non-seasonal differencing. Same way you can define the second order seasonal difference also. So if you have quarterly data, then 1998 first quarter value minus 1987 first quarter value will give you the first difference value, and then first difference of the first difference value at a season will give you the second order seasonal differencing. Now we need to continue this differencing as long as the time series becomes stationary. You can use seasonal as well as non-seasonal differencing on the same data set, because if the data has trend and data has seasonality, you may have to go for both these differencing on the same data set. So the order of differencing will not matter. So either you do seasonal differencing first and then non-seasonal differencing, or if you do non-seasonal differencing and then seasonal differencing, you are going to get ultimately the same series. Um, you need to continue differencing till your time series becomes mean stationary. So to achieve mean stationarity of a given time series data, you will have to go ahead with the differencing. And if your data is not variance stationary, then you can use transformation to make the data variance stationary. Now, once your data is stationary, so maybe it is d-order difference series, which is stationary, you will have to go ahead by fitting a model. And the Box-Jenkins methodology, or other name is ARIMA model, which is auto-regressive integrated moving average model. And it defines three parameters, P, D, and Q, where D is the order of differencing that we just now talked about. But this order of differencing D is the non-seasonal differencing order. Then here it is, the model assumes that auto-regressive, so it is a regression model. And since it is talking about auto means self-regression. So it is a regression model on self. So it will have a regression terms which are the regression is on the same series but the past time point values. So if you see in this equation, zt is your current time point, zt minus 1 is the previous time point. Zt minus p is p time period before current time period value. And if you get this, this is a kind of regression model of zt on zt minus 1, zt minus p, where p defines the order of auto regression. So AR in this model notation, AR, so the P denotes the or the specifies the order of autoregressive part. Now this Q talks about the moving average part, and it specifies the order of moving average. So on the right hand side of this equation you can see epsilon t minus 1, epsilon t minus q. So these are the error terms which are taken into consideration, and the model uses previous q error terms to uh, in the equation. And d is the order of differencing to make the data stationary. So this is d is the order of non-seasonal differencing, and epsilon t is white noise. So these error terms are called as white noise, where it will satisfy certain condition that the mean is 0 and variance is same constant, and the covariance between these two terms is 0. Okay, so these epsilons are IID random variables. Then they may not be normally distributed, but if they are normally distributed, then the terms epsilon t's are called as Gaussian white noise term. Otherwise, the assumption on epsilon t is that they are IID random variables with same equal variance. Okay. Now, in the left hand side of this equation, zt, we have seen that zt is d order difference series of yt. So, if d is equal to 1, we know zt will be yt minus 1. So, if you substitute the value of yt on the left hand side, the equation that you get will be in terms of yt, and then you will get ARIMA PDQ model for yt. So right now this equation which is visible on the screen is ARMA PQ model for ZT, where ZT is d order difference series. So this model, once you substitute on the left hand side for ZT in terms of YT, it will be ARIMA model, ARIMA PDQ model for YT. Alright. Now, what are the various steps in the model identification using Box-Jenkins methodology? So here is the first step, check whether the data are stationary. So this is the very basic crucial assumption in Box-Jenkins methodology. So whether the data are stationary or not, whether it is mean stationary or variance stationary. And if your data are not mean stationary, you will have to go ahead with the seasonal or non-seasonal differencing to make the data stationary. Then you have, if the data are not variance stationary, go ahead with the transformations and try to make the data stationary. Then you need to look at the autocorrelation function and partial autocorrelation function. Now, once the data becomes mean and variance stationary, uh, we have already looked at the definition also. The correlations or the covariances will depend only on the lags. So wherever the dependence is very high, those correlation values will be high. And that will tell you that whether the dependence of yt will be on which lag value. So when you plot the autocorrelation function and partial autocorrelation function, it will indicate which previous values the yt value, current yt value depends on. That will give you some idea about what should be the order or the values of p and q to be considered in the ARMA model. Now this p, d and q will talk about the parameters for the non-seasonal data. But if you have a seasonal component also present in the data which you need to model, you need to determine the P dash, Q dash values of the AR component and the MA component respectively for the season. That means in P, it will tell you that the dependence of ZT is on ZT minus 1, but P dash will tell you that dependence of ZT is on previous P dash seasonal values. So if P dash is equal to 1, that means ZT will depend upon ZT minus S, where S is the season. So for monthly data, if P dash is equal to 1, then ZT will depend upon ZT minus 12. For quarterly data, if P dash is equal to 1, then ZT will depend upon ZT minus 4. Since it's a quarterly data, you have 4 observations per year. So on and so forth. So, and same way you need to determine the value of Q dash depending upon what is the dependence of the error terms on each other. Now, as can see, this determination of these PDQ values will be based on the ACF and PACF plots. So sometimes it could be like a bit of subjective decision as to what value to choose, what value of P dash and Q dash to select once we finalize on the stationarity part. So it will give rise to different models, different possible models or different candidate models for your data set. Then which one to choose as the best model will be based on the AIC or BIC values, where these AIC and BIC are the Akaike's information criteria and BIC is the Bayesian information criteria. So these are the formulae just for the sake of completeness of the presentation I have written. But these values, Akaike's information criteria and Bayesian information criteria, are provided by the software, whichever software you are working with. So in R also, we will look at some examples. There you will see that these AIC and BIC values are provided by the software. So if you just talk about say 2-3 different candidate models, and then you need to pick up the model which is showing you or which is giving you the minimum AIC value. Okay. So now let us look at the demonstration. So auto.arima is the command which takes care of all the steps that we have looked so far. But right now, if you want to get some insight on what is stationarity, how this stationarity works, we will go step by step using the arima command, and at the end we will look at the auto.arima command in the R demonstration. So before we go for the R demonstration, just let me know if you have any questions. Okay. So let us have a look at the same data set, that is CO2 concentration data that we have used in the previous session also. And the data is already saved in the co2.ts. Now the command which is used here is the arima command, which requires the specification of the order. Now we understand this notation. C is used to denote the vector 1 comma 1 comma 1, which is P, D and Q. Okay. So if we look at this one, the plot of the time series, we all know that this is not stationary. This is not mean stationary. This can be variance stationary, but this is not mean stationary. So let us first difference this data. So if you can see this command co2.ts, so difference 1. So the command used for this is diff, if the original time series, and it talks about 1, that is the non-seasonal differencing of first order. Okay. And then let us look at the plot of this graph of the first order differenced series. Just let me know if you are doing it simultaneously with me, and if you want me to wait, just let me know. Just check if this you are able to get this graph. Okay, so here we can see that now in the previous graph we have seen that the mean was increasing with time, but now here you can see the data has become mean stationary. But at the same time we can observe that the pattern which was present in the data, that has not been removed. So this is an indication that there is seasonality in the data which was present is not being removed by this first order differencing. And to remove the remove the seasonality from the data, we may have to go ahead with the seasonal differencing also. If you see, it is this command where the first order difference series is now again differenced seasonally. So here the seasonal parameter is shown as 12, but the order is 1. And you can look at the plot of this series, which is first order. You can see it is first order differenced and the second order differenced series. And if you look at the plot of this, it is now mean stationary as well as variance stationary, and there is no repetitive pattern, visible repetitive pattern in this data set. Is it fine? Now let us have a look at the ACF and PACF of the original series to get some insight on how the ACF, or what is the interpretation of the ACF. So now this is the original time series data. So you can see that the correlation. So over here, when it is talking about lag, which is 1, 2, 3, 4. So lag 1 will talk about the correlation between yt and yt minus 1. Then lag 11 will talk about the correlation between lag 1 and lag 11.
Ma'am, auto dot arima function is not found.
Do you have the forecast library loaded?
Yes, ma'am. I think 1 minute.
Just check.
Okay, ma'am, understood.
Okay. Anything else? Anybody has any other queries, questions? Okay. So if you look at this ACF function, so of 11, so you can see that there is very high correlation in all the lags. That means all these values are very highly correlated. And again, this ACF is not going to zero. That means this is another indication, obviously, which we know already, that the data are not stationary. If you look at the PACF, when the data is not stationary, it is may not have any very significant interpretation as such. Now, once we difference this data, first order seasonal difference data, we can again look at the ACF and PACF of the first order difference series. You can immediately see the difference in the pattern, which is sort of sine wave curve present in this data. Okay. And then again, if we look at the partial autocorrelation function, again it is showing some pattern of say sort of sine wave curve in the data set. But if we see, so when it is a sine wave pattern in both ACF and PACF, and if we want to fit a model to this data, then autoregressive of order 2 and moving average of order 2 may be a good fit. And we can look at the first order difference series can be fitted with order C202. Why 0 over here? Because we are already considering a series with difference order 1. So if you try to fit the model, ARIMA model 2, and get the summary of this, so you can just see the CO2 difference first order difference model, which is fitted with ARMA 22. So you will get the estimates of AR1, AR2 over here, moving average 1 and moving average 2 parameters over here, and the intercept parameter. And it gives the value of AIC as well in this once the model is evaluated or fitted to the data. It will give you the log likelihood value also. Okay. So we'll just make a note of what is the AIC value for CO2 data when we are trying to fit AR ARMA 22 model to the first order difference series. Okay. Now let us have a look at, as we had observed previously, whether the data is stationary, the seasonality has been removed from the data or not. Then we looked at the first order seasonal and first order non-seasonal difference series. And then let us have a look at the ACF and PACF of these. So you can see that autocorrelation function is going to zero very quickly any values are not significant except few values. You can see significant spikes at certain values. You can observe the lower bound and upper bound given by the blue dotted lines here. Okay? And all the AIC values are within this range, indicating that the autocorrelation of lag say 2, 3, 4, 5, 6, etc. is not significant, but autocorrelation at lag 1, autocorrelation at lag 12, 11 is significant, indicating that there is dependence. Even after making the series stationary, there is still dependence of yt on yt minus 1 and yt minus 12. So the dependence on yt minus 1 suggests the value of p to be taken as 1, and dependence on yt minus 12 suggests the value of t minus suggests the value of p dash. So here I have asked for 24 different the values of till 24, but if we want to see whether there is still dependence on the previous value, you may have to go ahead with the 36 lags of the ACF. Okay, but we see that all the values of the ACF beyond 12 are not significant. Okay, so this indicates that the dependence, the P dash value dependence could be on one previous value and not only one previous value. Okay, so this will suggest you the value of P as 1 and value of P dash is also 1. Okay. The same time now to talk about the other part, we'll look at the PACF. And there are there are significant spikes available. So the number of spikes available in PACF, we'll talk about the order of P and P dash, and number of spikes available in ACF, we'll talk about the value of Q and Q dash. So here we can see there is a significant spike at 1. Again, there is significant spike at 12 and 13, rather 11, 12 and 13. Again, you can see there is some spike available at lag 24 also. Okay. So this may give rise to different candidate models over here for different values of Q. Now one model we can try and fit is the value with P and Q equal to 1 and P dash and Q dash also equal to 1. But now since I am trying to fit the model to the original data set, I am specifying the first order of the differencing non-seasonal as well as first order differencing which is seasonal. Okay, and period is 12, that tells you that it is a monthly data. Okay, so if we try to fit this model, ARIMA model, and then you try to get the summary. So since we are talking about ARMA 11 and for non-seasonal and seasonal ARMA 11, so it will give me 4 parameter estimates. 2 for non-seasonal and 2 for seasonal. So you can see S written before AR1 and MA1. Okay. And now you can see the AIC value is 87.11 as again the AIC value that was obtained in the previous model which was 372. So that means from amongst these two models, the best model is the one which that we have fitted just now. Yes, Santosh sir, I will do that. So which command you want me to post in the chat? all the commands? Yes, I have posted these commands. So here, the commands that I have posted is trying to fit ARIMA 111 model to the original CO2 data. And another command, a set of commands also I have posted in the chat box, which tries to fit a model to the first order non-seasonal and first order seasonal difference data. So I'll just wait for 5 minutes, and you can just execute these commands on your laptop and let me know if you have any queries. So you will have to have the forecast library loaded to run all these commands. The library is not loaded, you may have to, if the package is not installed, first you need to install the package, load the library, and then these commands will be executed. All right, anyone has any questions? Anybody else regarding the commands of ARIMA?
Ma'am, I think the command
Mm-hmm.
co2.ts underscore d1 is missing.
What is missing?
Ma'am, on applying this last command, then it's saying co2.ts underscore d1 is not found. Actually,
Okay, okay.
ma'am,
So it is the first order difference that you will have to execute. You can just check what is
yes,
the
ma'am.
command. What is that command? Here is the first order difference. And write this command.
Okay, ma'am.
I have posted it in the chat, anyways. It is the first order difference. And since it is non-seasonal, first one denotes non-seasonal and the second one denotes the order of differencing. It is the first order non-seasonal differencing. Yes, which graph? Tell me. The autocorrelation graph? Okay, done. Okay, fine. Yes. Now, if we look at the definitions of the autocorrelations, what do you understand by autocorrelation? See, auto means self. In this entire thing, whenever we are using this word auto, it is for self. And correlation means it is with itself. So, when you talk about autocorrelation of lag k, that means it is the correlation between the yt and yt minus k values. So when it is computed from the data, it will use, so suppose if we want to compute the correlation of lag 1, it will use y1, y2, yn minus 1 as one series and y2, y3, yn as another series, so that the difference in the lags is k. Are you able to visualize this, or uh, want me to write it somewhere? Are you able to visualize?
Yes, ma'am.
All right. So, whenever you talk about, yeah, whenever you talk about the autocorrelation, so this is the partial autocorrelation. Whenever you talk about the autocorrelation, have always the autocorrelation of lag 0 will be 1. Then at 1 you have some positive value. So this is the autocorrelation of lag 1 means yt and yt minus 1. When it is yt minus 2, so it is the lag 2 value. So if this value is significant, it will be above these limits. When these values are significant, autocorrelation values are significant, that means there is high dependence between yt and yt minus k, whatever the lag you are having. Okay. So in this graph, if you see, the autocorrelation of lag 0 is 1, then lag 1, lag 2, lag 3, all these values are very high, indicating that there is very high correlation between all the values. So here we are plotting it till say 24 values. So between lag 1 and lag 24 also the dependence is very high. If the data is not stationary, then the autocorrelation values will not go to 0 very quickly. Okay. So when in your this autocorrelation graph, autocorrelation function, the values are not going to 0 anywhere, indicating that the series is not stationary. All right. Now, when you look at the autocorrelation function of first order difference and first order non-seasonal and first order seasonal difference series, you can see that maximum values are insignificant. Maximum values of autocorrelation are not very significant, but few values are significant. So you have, this is called as a spike. You have a spike at lag 1, then you have a spike at lag 12. Okay, indicating that the dependence between those two values is very high. So yt is depending on yt minus 1, yt is depending on yt minus 12. So in your regression equation, regression means it is the ARIMA equation, which is auto regression equation. This information needs to be captured. Same way, what are the, how many number of significant spikes you have is important to determine the order of P, Q, P dash and Q dash. So the number of significant, so is this explanation sufficient? Santosh sir, or you want some more explanation? All right. And to determine the values of P, Q, P dash and Q dash, you need to look at how many significant spikes you have in ACF and PACF. So number of significant spikes in ACF will talk about the values of Q. Okay, so to determine the order of MA model, you need to look at the um number of significant spikes in the ACF. And to determine the value of P, you need to look at the number of significant spikes in the partial autocorrelation function PACF. Partial autocorrelation function is correlation between yt and yt minus k after removing the impact of the intermediate variables. So if you are talking about partial autocorrelation of lag 2, then it will be the correlation between yt minus 2 after eliminating the effect of yt minus 1. Okay, so it will solely talk about the correlation between t and t minus 1 without considering the effect of intermediate variables. The number of significant spikes in PACF will talk about the order of, will help you to determine the order of P. Fine? So this is to understand what is ACF, PACF, how to look at the values, etc. Okay, you can try different models. So you differentiate, so 12 comma 1, so it is seasonal differencing of first order. 12 comma 2, then it is seasonal differencing of second order. 1 comma 1 will tell you non-seasonal differencing of first order. 1 comma 2, non-seasonal differencing of second order. Okay, you can try to fit different models to this given data set. You can specify different orders for the original data set, as well as you can specify the orders for the different series also. Get the summary and check whether the, what is the accuracy looking at the AIC value. The best model selected will be the one which gives you minimum value of AIC. So once you finalize on the model which gives you the minimum value, for the AIC, once that model is fixed, you will have to go ahead with the forecasting. Okay. So forecast, you can just specify which model you want to choose and how many values you need to forecast. So if you look at this one, it will give you the predicted values and the standard error of the prediction. So since we have asked for 12 values, it is giving us the 12 value predictions of the 12 values using the predict function, the forecast. And if you want, you can find out the sum of squares also, residual sum of squares. You can check for the assumptions whether the errors are white noise or not. You can just plot those residuals. If you want, you can talk about the residual sum of squares also. For different models. And if we directly use this function auto.arima, it will take few seconds to figure out which is the best model, and you can see the best model given by the auto.arima function. So the series is CO2 series, and then it is not using non-seasonal differencing, but it is using first order seasonal differencing, and the orders P and Q values are 1 and 1. P dash is 2, Q dash is 4. So total 2, 6 parameters are estimated. So you can just see AR1, MA1, seasonal AR1, seasonal AR2, seasonal MA1, seasonal MA2. And if you look at the AIC value, it is 84.92, which is still little less than the model that we fitted manually. For us, the AIC was 87.11 for this model of C111 and 111 model. This model has little less AIC value. Yes, and if you want to look at the forecasts, so we are just trying to fit this model 3 with both seasonal and non-seasonal differencing the original data. We want to plot the forecast for ARIMA 3 model. It's going to plot it. This is the original time series and it shows you forecast for ARIMA, what model we have fitted for the CO2 data. The 12 is the seasonality that we have already mentioned. Period is 12 for the future. The values are forecast. And if you want to uh, look at look at the actual values of the forecast, you can just try to print those values. Yes, anyone has any questions or queries? I can wait for 5 minutes if you want to try these forecast commands in your laptop. Yes, I will paste the commands. Yes. So which one I have posted first previously? Forecast 3. Arena model 3. Okay. Yeah, I have posted a couple of commands in the chat box uh, to find out what is the summary of the model, how do you plot the residuals, how do you find the residual sum of squares, then forecasts, and plotting the forecasts. And you have other data sets also. You can practice it on your own for all other data sets. The readily available data set, as we know, it is A10. One of the data sets is A10, which is available, which is having both trend and seasonality. Let me know if you have any queries.
Dear participants, please let us know if you are okay with the codes and have queries or not.
All right. So there are few, like this is what I wanted to cover in the ARIMA modeling. The participants can explore themselves by considering different data sets. The basic commands are given to them. I have shared 3 4 data sets. Some data sets are available in the uh, R itself, R repository, or anywhere else. If you have any other data sets, you can uh, they can just use the data set and try different commands to gain the understanding of time series analysis. Now, there are certain other models for time series data depending upon what kind of. So, these are very basic models that we are looking at. Now, in finance data sets where there is a lot of volatility present in the data and that may not be captured using only ARIMA models. So, in that situation, we have the Garch model available for us, and it is basically the autoregressive conditional heteroscedastic. So these models will try to model the residuals where a lot of variability is present in the data. So majorly used in the time series. These kind of models will be majorly used in the financial data. And then you can have vector autoregressive models also. There are different methodologies going ahead, co-integration, Kalman filtering you have for time series data set. So as you go ahead, depending on the data set and the requirement, you can choose any model where you can talk about the cross correlations also. So if you have vector autoregressive models, then you need to talk about the cross correlations, and that is also available in R. So I think I was supposed to cover till the ARIMA models, but I just thought I will give the overview up till this. So this is also available.